Hello everyone, welcome to the presentation of our work titled Make a Story, Visual Memory Condition, Consistent Story Generation. I am Tanzila Rahman and this is a joint work done at UBC in collaboration with SNAP. Suppose we want to tell a story to a kid and want to generate temporary consistent stories based solely on the linguistic storyline. That is, we want to maintain resolution of references. For example, we want to address the characters by their respective pronouns instead of explicitly naming them in the subsequent sentences in a story. Moreover, we want stories to be consistent with respect to the subject and the background appearance. Here, the main challenge is that generative models are good at generating high quality visuals, but not at maintaining consistency. To address this challenge, we introduce Story LDM, a deep generative approach with autoregressive structure. To ensure temporal consistency and smooth story progression, we propose a novel memory attention mechanism which takes into account the already generated semantics of the previous frames. To validate co-reference resolution, character and background consistency, we extend existing datasets and evaluation matrix to include more complex scenarios. In this work, we leverage latent diffusion models to generate stories with high visual fidelity. Given a textual storyline, characterized by a sequence of M sentences, the goal of story generation is to produce a sequence of corresponding frames that visualize the story. We extend latent diffusion models to this task by allowing them to generate multi-frame stories autoregressively. For a given textual condition, latent diffusion model utilizes a cross-attention layer to capture the spatio-temporal interactions across multiple frames and sentences. For a story, we introduce a rich conditional structure that takes into account current sentence as well as context from earlier generated frames through our novel visual memory attention module. Our memory module takes the current sentence of the frame as a query and previous sentences as a key to weight the feature representations Z. The visual memory allows the model to incorporate character and background consistency and resolve text references when needed, resulting in improved performance. The final output from the attention module is the aggregation of cross-attention and memory attention modules together. Since reference resolution has not been studied in story generation, to validate our approach on this much harder task, we extend three datasets: Mugen, Flintstones SV, and Pororo SV. We modify the sentences by replacing the named entities with references where possible, including pronouns such as he, she, or they. We construct stories of 4 frames and corresponding text, ensuring consistent co-referencing in the story. For the Mugen dataset, we introduce 2 additional characters with 4 additional backgrounds. For Flintstones SV and Pororo SV, we reference characters by pronouns to generate a more natural story. To measure the consistency of the characters as well as backgrounds in the generated stories, we consider 3 evaluation metrics: character classification, background classification, and FID score. The table shows the quantitative results for consistent story generation. Our LDM baseline without the memory attention module is already better than Will's StoryGAN on the original reference-free text in the first and second rows. We observe that reference resolution makes the task considerably harder. Therefore, we observe a drop in performance of the LDM baseline in terms of character and background classification score in the second and third rows. Our model with memory attention module significantly outperforms state-of-the-art Will's StoryGAN by 41% on character accuracy. Similarly, on the Pororo SV and Mugen dataset, our method outperforms the strong LDM baseline with gains of 22% and 62% on character accuracy. Therefore, showing the advantage of the memory attention mechanism for consistent story generation. We now have a look into the qualitative results on the Mugen dataset. Rows 1, 2, and 3 show ground truth, LDM, and our story LDM approach respectively. Here we see that our method is able to maintain consistency in terms of both character and background. The results on the Flintstones SV dataset further validates the strong performance of our method when generating high quality, consistent stories. We observe similar qualitative performance on the Pororo SV dataset. We also compare the qualitative results of our method to both story generation and story continuation. Note that story continuation is a different and easier problem to address as it contains text with no references. The comparative images are taken directly from respective papers. Our approach that can resolve references and is solving a harder story generation task obtains highly competitive results. Furthermore, to show that our autoregressive visual memory module can generate diverse stories conditioned on the current and previous condition, we create different story lines starting from a single sentence in the figure on the left. Moreover, in the figure on the right, we show that our approach can not only generate consistent visual stories but also diverse frame for the same text. To conclude, in this paper, we introduce story LDM with a memory attention capable of containing consistency across the frames based on the previously generated frames and their corresponding descriptions. Both quantitative and qualitative results across datasets and a variety of settings show the effectiveness of our proposed method for the task of story generation. These are the references we used in our presentation. That's all from my presentation. Thanks to all.